Okay, our next speaker is Douglas Forman, NASA Ames.
Okay, yeah, Douglas Forman. I was the flight software developer for all the payload interfaces on Ladee, and was also did a lot of system engineering along the way based on the way we chose to implement things. And some other people listed there were other key members of Ladee that helped make this happen. And we're going to go over a little bit of what Ladee was, but not into too much detail, and the payloads and their different interfaces and constraints and requirements, and then the strategy we had for doing this integration of these payloads, and also the lessons learned, and also, if there's time, how some of those lessons are being applied to an upcoming mission, which is kind of Ladee-like. And so there's some lessons that are like, hey, this is good, we'll do that again, and some that are saying, well, this is a room for improvement. So I tried to highlight those in green or red as I'm explaining things that happen along the way. And so what is Ladee? What did it come from? Well, it started with, see, I'll use the mouse here. This hover test craft vehicle, which was basically no real requirements were put on it. It was kind of a rapid prototyping effort and a demonstration of Ames's ability to write flight software. It included using Simulink to generate code, using CFE so that the code generated from Simulink had to be adapted so that it could become a CFE application and communicate over the software bus, and included picking a ground station and to communicate to this hover test craft vehicle, which ended up being ITOS, and then showing that we could go through that cycle and develop software. Along with that, there was also a hill that was developed actually after the actual craft was there. A hill was developed in parallel to help with the testing, because it was a 3-hour. It was a couple of hours before you filled up the tanks, because it was compressed air to fill the tanks before you could do a run and drop it, and then try to stabilize it and see how that went. And then so I think Ladee was the first full flight software development for a spacecraft at Ames, and it did pretty well for its first time out. And the whole spacecraft ended up being developed at Ames with a lot of help from the other NASA facilities, especially Goddard. And we won some award with Popular Mechanics, showing on there as some Innovation of the Year thing, which was kind of exciting. And I think probably covered just about everything that's on that slide there, except for what does Ladee stand for? Anybody that doesn't work on Ladee want to take a stab at that?
Lunar atmosphere, dust environment.
You're close. Lunar atmosphere, dust. You're missing one word. So I have a little song that helps to remember what that is. I sang it last year. I made it for my kids. Model base, common bus, lunar atmosphere and dust, environment explorer. That's it. You missed the explorer part, but if I had a beagle bone, I'd give it to you now. That's good. So what were the Ladee payloads? There was 3 spectrometers. There was well, actually, I'm sorry, 2 spectrometers. I'll just go one by one. UVS is a spectrometer. NMS is a spectrometer. ALDEX was the actual, that was the ALDE of Ladee. That was the one that was actually measuring the dust, the ion detector. And then there was the Lunar Laser Space Terminal, the LaserCom. That was the kind of the big exciting one, because it was something that had never been done before, to have laser communication from a lunar orbit. And then the bonus payload, which I didn't even know it was going to be a payload, though there was talk about it, was the Star Tracker camera. Originally, it wasn't scoped in to have a camera on there. It wasn't, I guess, not in the budget or the design. But it was, I wouldn't say it was an afterthought, because I kind of, within the flight software, people were saying, there's a camera on there, we should make sure there's an ability to get the images down from it when we were designing the interface for the Star Tracker. And yeah, so this is a case where If you're just doing strictly what the requirements called for, we have never been able to take pictures because the requirements just called for getting the quaternion off of the star tracker and sending a time tag to it so we could sync up our times. Okay. In general, all the payloads had some things in common. There's going to be some protocol, hardware and software for getting the data between the flight software at CPU and the instrument. And then there's your typical things of data rates, and along with the data rates, there's some buffering associated, which may lead to needing flow control. You know, if the buffers aren't big enough, you need to be able to tell the other party, slow down so my buffer doesn't overflow, flow control. Then there's message framing. There's a bunch of data coming. How do you know when the data stops so that a message is done? And there's synchronization. Some of it can be in hardware, a pulse per second that you might send to a payload so that when you send it a time tag, it knows exactly when that time tag applies to. And then there's this RS-422 is a recommended standard. So within that recommended part, there's some room for variability, and like, is the termination going to be on the payload or on the flight software? That was something that had to be negotiated in the ICDs. And okay, so that's just getting the data from you to the payloads and back. That's the protocols. And then there's, of course, all the payloads wanted to get commands from the ground or stored commands, and they wanted to be able to send telemetry that would come back down to the ground. And another requirement was most of the payloads needed to have their software updated, so you needed something that was a rather large file upload that could get from the ground to the spacecraft and then over to the payload. And then along with that, there was each payload had some type of periodic message that you needed the flight software to send it, mostly something with a time tag in it, in some cases ephemeris data or attitude data. And actually that was only the one payload, the lunar laser. The laser comm needed to have a quaternion and a time tag because it was doing its own fine pointing, very fine pointing with the gimbal. And then besides that, the other requirements, like there's like just the state of health of the module that's talking to the payload. Like how much data, how many messages did I get from this payload? How many checksums may have failed on data coming from the payload, that sort of stuff. State of health, and some of that would feed into fault detection, because you could also want to be able to tell it, did this payload reset? How many times did it reset as we're on the dark side of the moon? So that stuff ended up being added kind of later in the game, not really too late. It was at CDR time, but that was kind of stuff that wasn't thought about in the initial prototyping. And then finally at the end, there's also like, you'll get garbage data coming from a payload on your interface. So we decided we needed to store all that and be able to downlink it if necessary, and especially in debugging. You can see what's this garbage data, so you could get that hex pattern that showed you that it was saying, this is the data explanation port, and then, you know, that sort of thing you want to. And it turned out we never used any of that unexpected out-of-band data, but it was nice to know it was there. Okay, so what the different payloads. I'm going to look at each payload and just show you what the interface was and talk about some of the key points. The UVS was just a straight-up RS-422 interface. And all of these will have this, there's an FPGA that implemented several UARTs and some custom data communication links that we needed. And we were running on a RAD 750. And so pretty much all the communication go through CPCI to this FPGA, and so there's just a standard UART to the UVS. And the UVS was a COTS product that had flown on Alcross, and it was kind of designed for somebody to type commands into, like, it was like almost an old modem. You'd type some commands and something would come back. And so it was easy to use interactively. It was a little more difficult to design a flight software interface around it, but we ended up designing something that worked, and worked quite well. So what we ended up having, and another decision we made with these payloads is I didn't want to have to know what every command to every payload was on board. I wanted the ground to be able to send it up, and I could put some wrappers or do something to it and pass it through. In this case, when you'd send a command, you didn't know what the size of data coming back was, because it had ACKs and NACKs. So I wanted to be able to handle it, and each command had a different length. Rather than putting that into the code, I put that into the API for the command coming up to the module that would say, I'm saying this command, and nominally I'd get back this number of bytes. And so I could just look at that, and if I didn't get the right number of bytes, I could increment a counter and put the data in the out-of-band data, et cetera. And okay, as far as one thing, a goal that we'd heard on, there's a whole talk about test like you fly like you test, for the guy from Berkeley did. And like, he got all the payload guys to use the ground system early on, and then he had, I guess it was Orbital, I think, doing the flight software. They also agreed to that, so that from early on in the mission, you're using the ground system to test things. So in this case, we actually had a unit from L-Cross, so we could start doing that early on, and we're able to write the interface so that we could go straight to the ground system early on enough so that before CDR, there was actually a whole software update on the UVS, and to do the regression testing, it was all done through STOL and ITOS. So by the time we got to INT, it was very confident that any problems wouldn't be in the flight software or even the ground database. There's any problems going to be with some kind of wiring or something else introduced during INT. Okay, moving on to NMS, the neutral mass spectrometer that came from Goddard. This actually had an interface called ITF, Instrument Transfer Frame. I think it's something that people at JPL came up with, but if you do a Google search, there's not like, oh, here's what ITF is, and hopefully it's not some proprietary thing that I'm giving away, but it's basically, this is a synchronous communication, so it has a clock that goes with it, and there's also a wire coming back from the receiver that says hold off on the data, so flow control. So it has data going out, coming back, a clock, and flow control. And so you can get higher data rates when you have synchronous communication. I don't think I put the data rate, but this was, oh yeah, 2 megabits per second. So this one was a little bit of a challenge, but not really that big a deal. We just had to put CCSDS wrappers on all the telemetry that came out and pass it down, and conversely on the way up data, we'd have to take off the wrappers and then send it over to the instrument. So we chose to do this as just a bent pipe, and that's kind of what we chose to do with most of these things, is treat it as a bent pipe for the most part. One issue was the big, when they wanted to do an image upload so they could load new software. Well, it turns out that the maximum size of CCSDS is 16 bits to the 16th, because they don't use 0 as a size. 1 is the lowest number. You can only get 64K in a message, and their uploads are potentially larger than that. So what we ended up doing is use CFDP to get the file up there, and then I had another interface, another command that they could send to say, send this file over to the instrument. So that was the case of there. It was just find a file in the file system and send it across. So that's how we dealt with that, and it was pretty simple. Okay. And then next, the ALDEX, ion detector, was pretty simple, RS-422. The only thing that they had that was different was that there's a pulse per second that they had, and they were using the pulse per second to match up to a time tag that we had send them so that they would know what the exact time that for synchronicity. So when they got the time tag, it was a little bit after that they had gotten the pulse. And so this was done by the guys out at LASP and University of Colorado. And I think they had done a lot of these before. It was they did a good job of making something that was easy to integrate with. This is probably the easiest one. Another thing, they didn't have any software uploads because it was all done in firmware. And they, what's that? I thought that. And I'll have to talk later. And the interesting thing, they also, there's not a lot of commands you need to send to these things. So they just had a limit, 1 command per second. And so part of there's no synchronicity they needed to do. It was just like each second, look, is there a command there? Yes, then they grab it and execute it. The thing coming back, though, wasn't as easy for us because we didn't know how much telemetry would come back. Every time they had a dust particle, we'd get a message coming back. So one of the tricky things was trying to get them during the early testing was like, send us the most number of packets you're going to send out of that. And we really never got them to trick their hardware into faking out sending more than like 60 packets in a second. So that was kind of a little bit of a risk, but turned out that it worked out okay. And there was they did have a lot of dust events. in fact, during the flight, there were so many dust events that they were thinking that something was wrong. So we actually, then this is what I heard secondhand. Karen was there live, and Nate were there live, but they did a maneuver, like a complete 180-degree maneuver, just to see that they're not getting dust particles hitting the ion detector, and they turned out they didn't get it, so they weren't false positive events. Okay, and I think I covered everything while we were looking at the picture there. So the bent pipe pass-through worked well. It was easy integration, RS-422. And then probably the most complicated one was the lasercom payload. They actually had two interfaces. One interface was for the control electronics, and the control electronics had a 2 kilohertz control system running to keep the gimbal pointed so they could keep lock on the optical signal. But anyway, the interface was simple, though. It was just RS-422. And it turned out that this was a brand new development, so we worked early on and on what the interface was going to be. Oh, it's my wife. Sorry. Sorry, I'm giving a presentation right now. I'll call you back. Thanks. Love you. That was unexpected. She's busy, though. I have to take her calls when she calls. I have a 5-year-old and a 2-year-old, so her to get 2 hands free to call is a big deal. Where was I? Okay, avionics, blah, blah. Yeah, so we could work together to develop the interface. In fact, that's what we try to do with all the payloads, is like early on, like a little over a year before CDR, we were talking about what the interfaces were going to be. So they used CCSDS. They also had the RAD 750 running on their control electronics. The custom hardware that we use for this upper interface was developed by the same vendor, Broadreach, so it made life kind of easy. And if you'll notice, this interface on the top is they gave us a little bit of their bandwidth from the lasercom to put flight software telemetry in. So we had a 40 megabit per second telemetry link to fill with data to send to the ground. I mean, 40 megabits, that's a lot coming down from the moon. So this was a synchronous data, and it looks surprisingly almost exactly like the ITF hardware interface, where we had the flow control and the clock synchronization. So one of the challenges on this, though, with the lasercom serial interface was they had like a 16-byte buffer. So we had the flow control issue, where I couldn't send commands to them too quickly because it would overflow their buffer and they would just miss the command, was what would happen. So they had a software signal coming back saying, okay, I'm ready for another command or next command. So I like keeping the picture up there, but I'll give you something to read. So the key things here, same advantages having the bent pipe. Oh, the advantage of this with the bent pipe too was that they could send all their commands, and they had their own ITOS database out at MIT, so that they didn't have to integrate their command and telemetry database with the flight software database. They had their own one that we could just pass through. And so from early on, from the beginning of the mission, they were working on their commands and things, because they expected to be doing a lot of tweaking and software uploads, tweaking parameters. And so they had that worked out early on, so that when they'd get their pass, they're like, okay, we're ready to go. We can do whatever we need to do to make this thing work. As it turned out, they didn't need to do a whole lot of tweaking. Things kind of worked somewhat smoothly from the very beginning. But they had that in place. And in fact, there's another. Actually, I heard this firsthand from the flight director, Rusty, that said that one day they did a pass and they did all their thing, and it turned out it worked great and stuff. And the next day, in the status update, they said they had uploaded a new software image to the payload. And he was like, wait a minute, that's something I'd like to know about before you do it. But it allowed them to work quickly and get things done. Basically, gave them enough rope to hang themselves with, or to make a rope to save yourself. Okay. One of these things I didn't mention, the synchronization, when we're using CCSDS, was that we're using packets coming over a serial wire. There's no sync pattern to sync on. If you start at the beginning and you get every byte, everything's good because you have a length field. You know where the next packet's going to be based on how large that packet is. But if you get off by a byte, then you're hosed for the rest of the time because you'll never find it again. So for dealing with these interfaces, and there was one on the Star Tracker as well. It was the same issue. We ended up just looking at in the primary header for the CCSDS packet. There's enough information in there to like form a little sync word because you know the range of the app ID. There's some other things that are always set to bits that are always set, and the length field you can kind of know what that's a range that's going to be in. So we kind of use that for syncing. And I did a lot of testing where I pulled wires out and put it back in to make sure that if we got out of sync, it wouldn't ruin a whole pass and lose all the science data for a pass. And this just talks about the high-speed data link. So what we did for the high-speed data link, this was a whole thing in itself. Like, how do you get telemetry for it? How do you fill that telemetry frame with meaningful data without interfering with all the other things you're trying to do, especially holding your attitude so that you can do this laser comm experiment? We have to have a really, really tight deadbands on your attitude control. So what we ended up doing was getting an FPGA design that would go into the flash memory and start at the beginning of where we have our file systems and partitions, and just byte for byte, just send all that data down. So we could send one partition at a time, or we could send all the partitions. And so we could send a gigabyte of memory, and it ended up taking less than 5 minutes to send a gigabyte of data. So, and in there, there's a partition for each instrument, and there's a partition for state of health data. So in 5 minutes, we could get all the data that was recorded on the satellite for the entire mission. But that wasn't the primary means of getting the data. Since this was an experiment, all the data that was also gotten down through CFDP with lots of procedures and testing that goes along with making sure that would work. And so this is just text that explains the implementation in more detail. I'll let people look at that later if they want to. I don't know. Am I about half done? Yeah, I'll go a little fast. Okay, the bonus payload, the Star Tracker camera, is just a regular RS-422 interface. This interface also allowed for bent pipe commands from the ground all the way to the Star Tracker and telemetry coming down. Yeah, so this is where that bent pipe allowed us to do things with it that weren't specified as requirements early on. One of the red thing there, one of the lessons learned was that the program decided not to purchase an ETU because it was kind of expensive. So all the coding done for this and the database development was done against a PDF file that described the interface. I mean, it was well documented. It was using CCSDS standard PUS, packet utilization standard, that was very well defined. So we got pretty close to doing it just based on the paper, but there were some things found on the INT floor that needed to be fixed. And even during flight, there was some other things found out that may or may not have been found out if we had it on the ground. We actually had it for like 4 days. We had one that was on its way to night sky testing, and it made its way to Ames. And so used that just to make sure that we could get data in and out with our hardware interface. And yeah, that turned out I needed the 3 days because the serial link, there was a problem with the FPGA, and had to take it out to our vendor that was building that FPGA to prove to them that the problem was on their side of the issue, where we were missing like 2 packets out of 100,000 packets. And then looked at their test results and found out that in their tests, if you look close enough, they were missing 2 packets, but that didn't rise to a high enough level for them. And the guy that wrote it was like, well, this isn't supposed to be reliable communication. He was citing the standards of this guy had a PhD on this stuff. And he's trying to convince me that's fine because it wasn't supposed to be. I was like, wait, no. Yeah, maybe if you send an infinite number, it won't get there, but I want it to be able to run for a year and not miss any. Anyway, so they fixed that, and we got the unit back, but we didn't have time to test a lot of the things we'd have liked to. Okay, a quick look at the Ladee architecture. This has been shown in some other presentations. Karen had this lollipop drawing, and this shows the software bus and how the apps communicate. The Simulink generated ones are up there in yellow. The blue ones are all the ones we got from Goddard that already had unit tests and were qualified for flight. And most of the ones that we had to write ourselves, which was in where I was at, were in this hardware I/O. So I'm going to blow that up a little bit, show the hardware payload I/O apps. There's one for, we decided to do one for each instrument. That way it was just easier to keep control of. I think originally in the original architecture before I was on the program, they just showed payload I/O, something that would talk to all the I/O apps. So we broke that up and it turned out to be a good idea because you could fix one, and you could, if we had to, you could upload one and not have to affect all the other ones. And this picture also shows the different messages that would be passed to who they're passed to, going through the software bus. And so the next, I'm going to kind of go quickly over the next ones. They're just kind of showing you how the message is passed. Like for initialization, here's how something gets, I'm missing something. Oh, okay. For initialization, a stored command comes up and tells the attitude control system, get into the mode for pointing for Aldex, for example. So it goes into the pointing mode. Then the stored command goes to the power control system, says turn on the payload. And then some more stored commands come out, and it passes a bunch of commands to the payload to get it configured for operation. And then after that, you're kind of just free running with telemetry coming out. And either, this is the live case, like LLCD, the laser comm. The telemetry is coming out live, and the commands are going in live from the ground. And state estimator is sending some quaternions in that get through one of these apps and get to into the instrument. And then, of course, most of the operations were done with stored commands and the data going in over to data storage. And then eventually, the files are all downlinked and they show up to the space science teams. Okay, so what was the strategy? I'm going to talk a little bit about what decisions were made and how they worked out. And I've talked about most of them before a little bit. So the first one was the decision first decision was not to purchase ETUs or EDUs from the payload. And this was done for a number of reasons, mostly cost and schedule. And after seeing the payload teams, they really didn't have the bandwidth to produce more than one or two of these things anyway. So it wasn't like only just money. It was a time savings. I mean, it just wasn't possible. So we decided to do this traveling roadshow, or some people call it a suitcase simulator, where I would take an EDU, early EDU, of something that represented the flight software hardware, and take it out to the different sites, plug it in, and see what it did, see if it worked. And then we do that, iterate over that a few times. And again, we did that a lot with the payloads. We went out there, but the Star Tracker probably would have been good to just put something like that in there. If we weren't going to buy it, to plan to go somewhere where we're going to do it and do more integration testing. And the other thing that was planned was to have a payload simulator that we would test against. Well, it turned out that was delivered too late to be useful for flight software development, but it was useful for integrated testing and also for the operators to get the feel of when you're testing and getting something that looked like payload data coming back out of it. Design decisions, I mean, the main big one was we wanted to do a bent pipe as much as possible, just pass data through these modules and get it to the ground and to the instrument. And then the other decision was to do an iterative development with the payloads. And this kind of goes back to what Bon was saying about, you know that these payload instruments are going to change because they're doing stuff sometimes that's never been done before. Some cases they've done a lot of these things so they can kind of have a good idea, but like the laser comm, they were, hadn't done something like this. It's going to change. So we decided to not require the requirements to be written in stone right away. So we along with the traveling roadshow, I guess I'll save that for the traveling roadshow. We iterated through the development and the requirements development. The payloads themselves, I mean, we tried to, as much as possible, get the new developments to conform to what we wanted for the interface to look like. Like, here's your set of app IDs and use CCSDS. But the ones that were COTS and were like, we couldn't really dictate to them because they were supposed to be COTS. Early integration with the ground software was done on most of the payloads. On some of them, there just wasn't the resources to be able to get them up to speed and have people to connect the ground system to them. So that was done rather late in the game, which caused some consternation when we're at INT and we've never really used the ground system to talk to the payload. I think there was one case of that, and it turned out to be fine, but I think there's people working extra long hours because when you're on INT, that's costing money. If you have 2 days to do something, you want to finish it in those 2 days. Otherwise, each day is costing 30 engineers, however much that costs if you're in the critical path. So it turned out to be okay, but I think it caused more stress than if we could have integrated that earlier. So this is the slide on the traveling road show, and the point here is that we had draft ICDs. Before the first time I'd go out there, we'd have a document. It was CM'd on our system, but it was not a lot of formality to it. The big formality was the safe to mate part of it. Before we plug these things together, we want to make sure we didn't burn anything out. So that went through a little bit more scrutiny. But the ICD was basically all right. There's what I think the data structure is. Somebody else would send me something. When you have something written down, and then I'd code something quickly. They had their thing that they're working on. We'd go out there, plug it in, see where the problems were, fix the problems, and then now the ICD now is not what you wrote down. It's the working prototype. Then we had modulate that or back to the document. So now the document matches a working prototype. Yes, question. Oh. Okay, which HW is hardware, IF is interface, ICD is an interface control document that defines what the messages look like for data. Any other ones up there? SDU is a software development unit. Engineering development unit. So this is like a cheap version of your flight software. It's your flight hardware. In our case, they're PowerPCs. So like for MIT, the first time I went out, I took, I was going to say that one, but I figured I already had enough laughs going. So, sure. Thank you. Thank you for letting me clarify that. So we actually took an EDU out there that had an RS-422 card off the shelf in a CPCI chassis, and we left it there. And it had, I don't know what that means, but it's a standard compact piece. Compact, it's a
modification of the PCI standard.
It's basically, what you have inside your PC, the interface for putting cards in and stuff. It's a compact version of that. So it's pretty standard, and the cards are pretty inexpensive as well. So I took that there, we hooked it up. We worked till like 2 in the morning until we got the commands and telemetry coming out. And, oh, by the way, if you have a visitor's pass at MIT, don't stay there till 2 in the morning. After 6 p.m., your badge doesn't work, and a bunch of security guys come out, and your escort gets in a lot of trouble. And it's kind of exciting. But, that's a different lesson learned. But the point was, I left it there. We got things kind of working. And this is just rough software. I mean, I hacked it out quickly just to get it working. I had like multiple tasks. Just anytime I was doing something in parallel, I'm just like, I'll make a new task for that, whatever. So that got cleaned up and requirements written, and the whole thing, software written and tested. Okay, now I have new software. It matches all my requirements, and it's been through code review, but does it still work with an actual payload? So then I could send it out to him. He'd run it on his thing and say, yeah, it works. And so, or, I have what happened to this feature you had here? What happened to that little feature you had? It's like, oh, that didn't make it into the requirements. He's like, oh, I kind of like seeing that. So, okay, then we go back and make a requirements change and put that in there. So the whole thing was kind of, in a sense, kind of an agile type of approach, because the traveling road shows were like a sprint. And there's only me and the guy on the other side. And this kind of goes back to the keynote thing where he was saying, if you take system engineering out of the way and just have 2 guys working on both sides of an interface and let them work at it, it's more efficient. And that's kind of what we ended up doing to get all these interfaces together. Just find the point of contact on the other side that's actually implementing it, and you guys work on the ICD and actually working code where your 2 machines can talk to each other. Okay, so that's that. So then I probably covered all these throughout, but this is just a summary of the lessons learned. The bent pipe approach was advantageous. It allowed tests like you fly with the ground system, since we could, since I don't know, you're probably all aware that CFE uses CCSDS so that anything you put on the bus can come to telemetry, and commands going up also are in the same format that your ground system sends up. So the software logic was simpler with a bent pipe, and it gives the power to the payloads teams for commanding. And oh, here's another lesson learned was COTS, I should put that in quotes, / legacy does not preclude modification. Because it turned out, like, since this was our first flight software project, we didn't have a lot of credibility. We're like, you know, the rookie in the NBA that gets hacked and they never call a foul, but, you know, if you're like, you know, Michael Jordan, they blow on you and there's the foul there. You know, so we were just like, they said it's COTS and this interface can't change, so, you know, that's what we worked to. We didn't push back on different things, but it turned out like one of the payload interfaces also flew on Maven. When I talked to him at the end of the mission, he goes, "You guys are too nice. You didn't actually ask us to change anything." It's like when we've worked with Lockheed Martin, their software for interfacing over the RS-422 that they were using, what was reused, used the IP protocol. So we had to actually add to our software around the ITFs an IP protocol, and on both sides of it. And so you know, the lesson learned was you can push back on these payloads, and if it makes sense, they can pull off a CCSDS wrapper off their data or put one on just as easily as you can in your flight software. And it also would allow you to get this bent pipe working earlier. In fact, the next mission that I'm working on, we're designing it, since we don't have the EDUs yet, we're designing it so that we can connect ITOS directly to the payload early on, like the Berkeley guys are doing, so that we can get end-to-end before we even have anything in the middle. So we can get end-to-end and then put the flight software in the middle. Okay, so some of the, and then of course iterative development works well, blah, blah. Okay, I think I covered all that. And then the red ones to review were that, oh, I didn't cover this red one here. So part of the I think it's here, is log data analyzed. Part of the informality of this was that there was not really a big test plan. It was like, we'll get data to talk to each other. I end up creating a file, and we download it and give it to the payload guys, and they look at it, and they tell me, it's good, our payload worked, you know, everything's in there. And I was like, all right, you know, so that was pretty much the extent of my saying that it worked well. Well, it turned out one of the payloads on the INT floor was saying, like, they were missing a command out of all these different commands. The command wasn't getting through. So and so on INT, it's like, well, is it a hardware problem? Is it a software problem? Is it on my side? Is it on your side? And so we went back to the log data from the traveling roadshows, and he looked at it and he goes, "Oh, it was missing the command in the traveling roadshow like a year ago," and it hadn't noticed it because it hadn't risen to the level of. I'm not sure exactly why it wasn't noticed, but it was noticed at INT. So now it became my problem because it's a bug in the flight software. And you know, you have your 1 or 2 days to fix it, or else it's going to start costing a lot of money. And it became a little stressful. We ended up, the bug turned out to be, so we had, for this interface, we had a synchronous protocol, and we had a 0.5 megabyte buffer, or was it a megabyte? It was huge. So we were thinking, well, we don't need to, and the flow control was done in hardware, so we don't need to, you know, it should work fine. We don't need to do a big deal. Well, the problem was that it's fine, you have the big buffer, but if you had 2 commands going quickly, or 2 pieces of telemetry coming out quickly, yeah, this wasn't I'm sorry, it wasn't a missed command, it was a missed telemetry message. And sometimes they would come out quicker than others, like the printf type event could come out rather quickly. So that's what was happening, is we were getting a command too quickly before we could, there's 2 buffers. So it was a buffer swap issue, but by the time we swapped buffers, we'd missed a command. So, and the problem was in the driver, and the flow control wasn't working proper, wasn't in the right place to hold off between data that was coming down. So we had to get the scope out and look at all the messages, and after a couple days we could apply the fix, but it was a little bit stressful. But the good news was that there was no hardware interface problems found in INT, which would mean you have to pull things apart, and that would have been bad. And lastly, of course, I already mentioned this. Not having the star tracker was a risk that was realized. And then the lessons being applied, I've already mentioned, I think, all these as I went along. So, any questions? All right. Thanks.
Questions? Yes. Wait.
You mentioned the problem with the PUS standard packets and ITOS. Can you describe that?
Well, and this may not just be, it may not be an ITOS problem, but it may be a problem with the database, the way it's implemented. But let me just say that ITOS, the way we're using it for everything else, and the way CFE kind of uses CCSDS, the packets are fixed size. So you have and they're fixed, meaning like you have an app ID, it has a fixed size associated with that. So the database for ITOS, when it sees an app ID, it knows how the packet is laid out based on the app ID. So with the PUS, of course, you have one app ID for your instrument, and then there's secondary headers that have codes in it that tell how the data is going to be laid out. And it also can be variable size. So that turns out to be a little bit harder for ITOS to deal with, but it can be dealt with, and I didn't deal with it because I ran into the problem of doing that, and I was like, this is too much database work for me. I need to focus on the flight software. So I ended up just dumping the data and then writing my own little parser to grab what I needed out of it to make sure it was right. But mostly, what I was on the flight software, I was grabbing the data, getting the quaternion, and passing it to the state estimator.
Great. Other questions? Great. Thank you.